I'm Alexander Schreifer. Currently, I'm working in JetBrains Research, Programming Languages and Analysis Tools Lab. In this video, I'm going to present you my thesis work dedicated to integration of the offline partial deduction in the functional conversion for relational languages. Relational programming, or pure logic programming, is a paradigm in which a program consists of predicates instead of functions. This property allows users to solve multiple problems with a single program. For example, having one program which implements verifier, we can also provide a solver. This problem is also known as the verify-to-solver problem. I illustrate it with the example of the evaluator of logical formulas. In one direction, this evaluator can produce the value of the formula. In the other direction, it can generate formula by value. This solver, however, will be inefficient due to the interpretation overhead and non-optimal order of the clauses. This leaves room for a variety of methods, from sample execution to the rearranging of clauses. The family of these techniques is called specialization methods. The goal of my research is to explore ways of combining these approaches in order to achieve better quality of specialization. Here I present some works which previously made a contribution to a related field. The first two papers show that partial deduction can be considered as an effective instrument for eliminating interpretation overhead, while the third paper proposes mode analysis and functional conversion as instruments which improve performance by extracting statically known information about the relation call and transforming it into a functional form. These proposals represent different approaches to solving the problem. We could possibly benefit from their integration. The goal of my research is to develop a more powerful technique by combining previous approaches. The steps of my research are to analyze common specialization techniques in logic and relational programming, to tune the most suitable approaches to suit our goal best, implement a transformation methods which combines specialization and functional conversion, to collect benchmark suits and evaluate the proposed approach. At the moment, the algorithm workflow is as follows. Mode analysis and binary time analysis extract statically known information about the program and its arguments. This information is then propagated to the next phase. The program transformation is continued by partial deduction, which simplifies the relational program by using the results of the previous steps to specialize the program. Transforming the residual program into a functional form concludes the algorithm. At this point, we have only done a limited evaluation of our approach. Here we present the comparison of the described transformation with functional conversion and the online partial deduction algorithm. I measured the new approach on the DPPD library of benchmarks and some verify-to-solver examples. In the already discussed example of the propositional evaluator, the proposed approach shows improvement compared to the functional conversion with mode analysis. However, due to the lack of accuracy of the preliminary analysis, the algorithm does not yet show better results than the online approach. The classic Tower-Aharonov puzzle is another example of the verify-to-solver approach. The verifier program checks by the given sequence of disks moves if the finished state can be achieved from the start state. My goal is to produce a program which will generate moves needed to achieve the finished state. The results of comparison in case of Hanafi tasks show 5-order magnitude improvements of the execution time of the obtained solver. The DPPD library of benchmarks is an open source library which consists of examples of logic programs. This library is basically used for comparing partial deduction approaches. The examples are written in the Prolog language, because of which some of the programs contains functionality that is not supported by Minikanaren. For this reason, we only use a fraction of the benchmarks. For most of the used examples, we observe improved or the equivalent results. However, the further improvement of the pre-processing phases promises to yield results. In conclusion, I will sum up the work done. I surveyed and adapted the relevant techniques for my task. I collected benchmarks used and conducted a preliminary evaluation. In some benchmarks, we got some promising results. However, we also observed the lack of precision of model analysis on a batch of examples. Taking into account these facts, the main goal of my future works are to improve the quality of the model analysis stage and to finish evaluation.